All right, so today, of course, we're going to finish up Unit 4. We're going to finish up Unit 4, and then we'll see how far we can get in Unit 5 here. All right, but kind of as a checkpoint for yourself, apologies, kind of as a checkpoint for yourself, you know, tonight might be a great night to get caught up and get all of Unit 4 finished here, all right, because we only have today and tomorrow, and then our weekend. And that's pretty much it, right, in terms of things that I'll send out to you, because then the rest, all of next week, again, is, remember, your solo week, and we'll talk more about that tomorrow. But again, just a reminder that you've only got a couple days here left if you really, really work hard here, so then you can have all next week off. So again, keep that in your head. That should be kind of your ultimate goal here. All right. So if we actually look at Apex here, share this. All right, we got through 4.6 yesterday, which was, again, of course, evaluating reports. So now we are on our last new unit, which is 4.7, applications of statistical techniques. All right, and so, of course, with this one, there's this one quiz here, and then there's this extra credit practice if you'd like. And again, reminder, you can get partial extra credit points if you try this. All right, so what I was gonna do here is I'll fly through this pretty quickly here, because again, we've been talking a lot about stats, we've been talking a lot about specific examples here, and so I think that this is kind of a good wrap up for us. So I'll try to kind of go through this quickly, because what I really like is, of course, obviously for you to go through this at your own pace. Really make sure that you're answering all these questions and that you're understanding what's going on here. But of course, I'm going to try to explain this unit quickly so we can wrap up unit 4 here. Okay, so if we look here, this first example is talking about sodas, right, and a soda bottling company. All right, and so they're saying on average the soda produces 8 ounces of liquid. All right, 8 ounces of liquid. However, because the factory's machinery is old, there is some variation, right? And so what it's saying is some sodas have a little more than 8 ounces, while others have a little less. On average, there's 8 ounces with a standard deviation of 0.2 ounces, okay? And it's asking you, how could you prove that there are fewer than 8 ounces of soda in each can? Okay, what we could do here is we could take samples of different sodas, right? Grab different sodas off the assembly line, and we could calculate the average amount in each of those sodas, actually measure out the number of ounces that are in that soda, okay? And then we can use statistical analysis to prove that there are, you know, this plus or minus 0.2 ounces, okay? We could prove that. All right, and this is saying in each can here, right? So it's saying it's kind of a repetitive thing. It's not just a one kind of fluke here. Okay, and then of course yesterday we talked a lot about these different parameters in your experimental design. Again, experiment being a loose term here, just because we're totally designing something. It doesn't have to be, of course, science-based, right? It can be based in anything, as long as you follow the kind of rules we discussed yesterday. All right. So we have those 3 parameters here, basically the control, randomization, and replication. And they all have their own purpose and their own reasoning. All right, control being, of course, we need to make sure that it's only the testing group that has the results. So you need somebody who is not the testing group also to take part, so that you can collect their kind of negative results here. And under control, we talked a lot about the Hawthorne effect, which is where patients act differently knowing that they are taking a study. And we talked about the placebo effect. So people having false positives with things like sugar pills instead of the actual medicine that's being tested. All right. Then we talked about randomization. So a lot of that has to do with assigning random numbers or not knowing who's in what testing group. Again, trying to eliminate the bias. And then obviously replication. Okay, you've got to be able to repeat your processes. And if you can't repeat your processes, that talks a lot about either the nature of the results. It talks about the experiment, how well it's made or not made, or it talks about your communication, right? Can you communicate that to somebody else so that they can run the experiment as well? All right. So if we look at these different factors here, taking a measurement randomly at random selected points throughout the day, that would be an example of randomization. Okay. Repeating a study 10 times, that would be replication. All right. Testing patients by either giving them a new drug or no drug, that would be an example of a control or having a control. Same thing with studying the effects of both having therapy and no therapy. That's an example of having a control. Performing 5 different studies on the same drug, that would be replication. All right, and then assigning test subjects to group at random would be another example of randomization. Okay, so just pulling that kind of stuff out quickly is going to be helpful for you because, again, of course, it's going to tell you, it's going to give you insight into whether or not a test is valid here. Again, is it done well? Okay, is it done well? So, of course, when we're designing a study, when we're designing a study, we have to take those into consideration as well, not just experiments. However, studies can be slightly different, right? We talked about studies can be more along the lines of surveys, personal opinions, right? Questionnaires you pass out, things along that line. Okay, but it still has different elements to it, right? It still has different elements to it that are important. All right, and so if we look at this scenario here, sometimes some scientists think they discovered a new drug that will help salmon grow larger. If it's true, local fishermen may be interested in this drug. Okay, so scientists could conduct an experiment to identify, and they want us to identify the different elements of the experimental design. So if we look at this salmon drug here, okay, they want to test whether or not a certain antibiotic causes salmon to grow bigger. They apply the principles of good experimental design. First, they randomly select a group of salmon that will be the subjects for the experiment. Okay, great. So they selected random salmon. All right, then it says they go to a number of different locations where salmon swim and catch the salmon at different times of day. This procedure ensures that the salmon are chosen for the experiment are chosen randomly and that the sample accurately represents the total population, right? So again, totally different locations. So they weren't just looking at, maybe one part of a stream, okay? And then they also picked it at different times of the day, maybe because larger fish come out at different times, who knows? All right, so that's good that they did it randomly here. All right, back at the lab, the scientists weigh the salmon in order to get data on how much each fish weighs before the experiment starts. Okay, so that's really, really good. That's their starting weight. All right, and that's going to be very important here. Okay, then obviously half of the fish get the antibiotic, half of the fish don't get the antibiotic. The second group that doesn't get the drug is the control group. Of course, this procedure will allow scientists to compare how fish develop and grow without the antibiotic. All right, and we'll look at it in a second because it's saying they randomly divide. Okay, so that would be something that of course I want to know more about. How did you randomly divide them? Especially when you look at this graphic here, because it looks like they picked the bigger fish to have the antibiotic than the small fish. All right, but I'm assured that's not true. All right, but after the antibiotic or non-antibiotic, right, the set amount of time here, they're going to measure both fish. They're going to measure both fish, both groups of fish here. Okay, and they're going to see how the fish responded. Okay. At the end of the experiments, the scientists weighed the fish again and compared the average weight of the fish from the two groups. It's important that the scientists repeat this multiple times in order to confirm the differences they observed and not just a result of sampling variation, right? So they measured, again, of course, the average weight of the fish. Okay. And something that they could have also done is that they could have taken the difference between the starting weight and the ending weight, right? So that's something that they could have done. For each of the fish, if they randomly assigned them, they could have taken the weight here and seen how much weight they gained, right? That's another way of looking at this. Okay, but if we noticed there in the salmon experiment, all 3 design factors were considered. Okay, they selected them randomly and put them randomly into groups. They had a control group because one got the drug and one didn't, and then they repeated it several times to check for the same results. Okay, so that's our 3 main parts there. Okay. And of course, I can't stress enough how important it is to design an experiment correctly. Otherwise, the results of your experiment are either inconclusive or they're false, right? You can't make conclusions based on a poorly designed experiment. All right. So if we look at this example here with energy bars, okay, so it's saying to test the effectiveness of energy bars on working adults, researchers selected a random sample of 100 people, all of whom were working adults for an experiment. The subjects were instructed to come back to a lab before work. All right, the 50 people who arrived were given, the first 50 who arrived were given the energy bars and ate them there before going to work. The last 50 who arrived were given fake energy bars and ate them before work. Researchers then called the respondents at noon and 5 to ask them how energetic they felt, right? This experiment was repeated multiple times with different samples, okay? Is there any flaws in this design of the experiment? Okay, and hopefully you saw it as soon as I read it, okay? They gave the first 50 people the energy bars, okay? And that might be bias here because it's not really random, right? Maybe it's a personality trait of people who get up early, right? That it's more indicative of a behavior with energy, or they're ready to go, they're ready for their day, versus someone who's running late to something, right? Or kind of the last people to get there, right? So that might introduce some bias. So when they ask them how energetic they felt, right? Maybe the last 50 people already weren't feeling energetic that day because they were running behind. And so now you've introduced this theory, or this concept here of bias, this new concept of bias. All right. Another one, of course, so this one, of course, you could just say suffered from a lack of randomization. Okay. So if we look at this one here, you think your classmates will do better on an upcoming test if they study 4 times a day for 30 minutes each time instead of studying once a day for 2 hours. Okay. You convince the entire class to study this way for the upcoming test. Okay. After the test, you compute the average scores. Is there any design flaws? And the answer is, of course there is, right? There's no control group. Everybody in the class is taking the test the exact same way. So if everybody does really well, you have nothing to compare it to. It may just be the fact that the test is easier, that you guys all understood the material, versus if you had half studying in each way, you could really test out, okay, well, is it the test itself, the material? Is it the actual study method, or is it something else? All right, so you could kind of flush that out with that design. So of course, then if they had no control group, right? There was no control group. Okay. And because there's no control group, there's no randomization, since every student in the class was asked to try the new method. Okay. And I love this. When your sample is the same as the population, you don't need to worry about randomization. Okay. So what that's saying is if you're able to ask every single person that you're trying to evaluate, right, your entire testing group, all right, if you're able to ask your entire testing group to do it, you do not need to worry about randomization because you've asked everybody, right? So same thing. It's like saying, if we wanted to put something in at St. Lawrence, right, you could either randomly ask students, where you need to make sure your randomization is correct, or you could ask the entire school, making sure you ask every single person, right? So that is potentially an option. And if that's your option, right, you can take the entire population. You don't need to worry about randomizing your sample, okay? But again, of course, the last one really lacked the control. Okay, it really lacked the control. And the other thing that it lacked that wasn't as glaring of an issue is replication. Okay, replication, right? So again, going back to how do we know that it's this testing factor or you know the factor that we're looking at versus just a one-off fluke here as a result of something. Okay, so then of course it's looking at this practice here. We'll do this one together. So to determine whether laboratory mice really do like cheese more than other food, a biologist gets a simple simple random sample of mice. The mice are randomly selected one by one to be put in a cage containing several different types of food, including cheese. All right, the first two mice immediately go for the cheese, so the biologist stops the experiment, stating that this is conclusive enough evidence that the mice do like the cheese the most. Okay, I would say this suffers from repetition, right? Two mice don't make a pattern, right? Two mice don't make a pattern, and especially because it was the first two mice, right? So what if the next 10 mice that they study go towards something else that's not cheese, right? So you need to be able to repeat that. All right. Looking at potato chips. So to determine whether students like a new brand of potato chip better than other brands, market researchers randomly select a group of students who will rate the taste of the new chips. The process is repeated multiple times for multiple students. The researchers look at the rankings and conclude that the students do like the new chip. Okay. So it looks like they have randomization because it says researchers randomly select. The process is repeated multiple times. So the question is there a control? And what would that control look like? Right? And the answer is no, because students never rated the old potato chips, right? So again, it's all about before and after. So maybe they really just like this brand of potato chips, so they rate the old bag as a 10 and the new bag as a 10. So there's really no improvement there because they never asked for the original opinion. Okay, and then finally here with cups of coffee. Okay, researchers want to determine whether people like a brand of coffee better than the old brand. So they prepare 100 cups of coffee, 50 of the new and 50 of the old. They obtain a simple or random sample of 100 people who were instructed to come to the lab at a certain time for a taste test. The first 50 people arrive, taste the new coffee, next 50 people taste the old one. Okay, so right there immediately, that does not have randomization. It does not have randomization. Okay, other factors could take into a place. So again, who arrive first, maybe there's something about how much they like coffee if they are first in lines, or there's other human factors that might affect that. All right, so that one really lacks from randomization there. Okay, and then of course here I'm going to let you guys do this problem, how much soda's in the can. All right, I'll let you work through that problem so that you can understand what's going on there, right? And basically what it all really boils down to here is we can take a sample of our cans, right? So a random sample, and they said 36 cans of soda. All right, 36 cans of soda. And pardon me, sorry. Whew, hiccups. So what you can do then with your 36 cans of soda is actually measure out how many ounces are in them. Okay, and it turns out that on average there's only 7.7 ounces of soda. All right, but the company claims that it puts in 8 ounces of soda with a standard deviation of plus or minus 0.2. Okay, so even if we were at our 8 ounces of soda, minus 0.02 doesn't even get to the 7.7 ounces that this company is claiming, right? So obviously here there's a little problem that we need to solve out here. All right, and of course we got less than our expected mean. Okay, so it could be evidence, right? And I love that they said that. It could be evidence that the company does not put 8 ounces of soda on average in their can, or this could just be sample variation, right? We only grabbed 36 cans of soda. All right, so maybe we grabbed a bad batch, right? Or maybe we didn't do a very random sampling here. All right, so just because we got a result that didn't match up with the original does not mean we can automatically conclude that the company is lying here, right? It could be an indication. However, we got to do more tests to figure it out here. All right, so we can look at our variation. Okay, so beyond our 7.7 ounces measurement, okay, we can look at our variation here. All right, so what we can do is with samples of more than 30, right? So we have to have more than 30 samples. We can look at our sample standard deviation of the distribution of sample means. All right, or again, looking at our distribution here, we can have our standard deviation is equal to sigma over n, where again, n is the number of objects. All right, and when we look at this here, we can take a look at our calculation. So, of course, we can also do other things like constructing our confidence interval, right? Our confidence interval. And that's our average value plus 2 standard deviations, right? Plus 2 standard deviations, all right? And based on our data, our standard deviation will be this 0.033. Right, our standard deviation is at 0.033, and that means that our sample mean here for our confidence interval is between 7.9 and 8.07 ounces. Okay, so if we look at our confidence interval, okay, again, it's saying we are really confident, 95% confident that the data falls between these 2 points here. All right, that's what the company's reporting out when they say 8 plus or minus 0.2 ounces. Right, they're saying, all right, 8 is my average number. All right, so what we can do, of course, like I said, is take that 95% confidence of how good do they feel about this value of 8 that they're reporting out. All right, and of course, like we said, since it only goes down to 7.9. 7.7 is way outside of our expected range here with a 95% confidence. All right. So if we look at our confidence interval, okay, if we look at our confidence interval and our value doesn't fall within there, within a 95% confidence, okay, that implies that the company is most likely being dishonest here. Right, they're most likely not putting in the 8 ounces as they suggest here. Okay, and again, that's based off of our confidence interval and our 2 sigma factor here. Okay, or our 2 standard deviation rule. All right, and of course, it's always great to highlight that replication might be an error, so it's always good to maybe try it again on another day, have somebody else do it to make sure that you're not biased, whatever. But of course, replication is a huge factor that should be taken into consideration here. Okay, and so that example is one that really tests population, right? It really tests the population parameter. All right. So if we look at another example here, we can look at the light bulb lifetime, right? So how long does a light bulb work? Okay, it manufactures to last 150 hours on average with a standard deviation of 1 hour, so plus or minus 1 hour. Okay, you take a sample of 64 light bulbs and you find that the average lifetime of a bulb sample is 149.8. Okay, So if the light bulbs in fact do last the 150 hours on average, what would the expected mean of your sample of 64 bulbs be? Okay, so we don't need to do any math for this first question because it's saying, what is the expected mean? Well, mean and average are the same thing here. All right, so our expected mean is, or our expected average is the 150 that the company says that the light bulbs last, right? So this is our expected mean value with this little U here. Okay, so this is the value we'll use to create our confidence interval to check and see if our point is within our confidence interval. All right, so we can look at our standard deviation here. Of course, our standard deviation is 1 hour, right, based on what they told us. So sigma here is 1 hour for our standard deviation, okay, of our population. All right, and then we can put it over the square root of 64 because that's how many light bulbs that we tested. All right, and this leaves us with an overall standard deviation of 0.125. Okay, and let me really highlight here a difference. This is our standard deviation of our sample, right? Of our sample, the sample that we've taken, versus sigma here, right? This sigma here is the population standard deviation. So it's what's reported out to us. Okay, it's the value that's reported out to us from a company or from a box or something along those lines. Okay, so this is talking specifically about our standard deviation for our experiment. All right, and then the last step for us is to be able to create the 95% confidence interval after we have this standard deviation value of 0.125. Okay, so of course, now that we have our 95% confidence interval, or I'm sorry, now we need to calculate our 95% confidence interval, right? And it's the same equation we've been using. So 95% is our average plus or minus 2 standard deviations, all right? And we calculated our standard deviation to be 125 or 0.125, right? So 2 times that gives us this 0.25 here. All right, so our confidence interval, we're 95% confident that all data will fall plus or minus 0.25 of 150. So all the way down to 149.75 and up to 150.25. Okay, so if this is what we can expect here, and our samples had an average of 149.8, what does that mean about our experiment here? Okay, what does that mean? So again, our sample is inside the confidence interval, which means that these bulbs do last 150 hours on average, right? What they were claiming was true because our data also fit inside their confidence interval. All right. Of course, it says here, but as a good researcher, you will repeat the experiment. What if in the next experiment you find a mean of 149.5? Okay. So what could we conclude then? What would we do next if we got a value that was outside of our confidence interval? Okay. So if it falls outside of the confidence interval, we should do a few more experiments to make sure that our data is true before we come to any conclusion. Right, so that would be saying we have 1 positive test, 1 negative test. Well, let's do another one, repeat it again, see what happens. And then, of course, always go back and check to make sure that you didn't change any experimentation parameters between the first experiment and the second experiment. Like, was it a different time of day? Was it a different light socket? Did you test the bulbs differently? All of that kind of stuff. Okay, so that's really walking through an entire problem there. And going forward here, this one is looking at 2 different reports. All right, this is about looking at two different reports here. And I will let you guys go through this one as well on your own here. I think it's a really great example. It walks you through the different steps like I just did. Okay, so to kind of wrap this unit up here, it's important to reduce bias by doing controls, repetition, and randomization. Okay, and under what circumstances do you reject a survey claim? right? And that would be if it falls outside of our 95% confidence interval, okay? That would be if it falls outside of our 95% confidence interval, all right? So of course, obviously, that requires us to calculate our standard deviation first, and then look at our average value, or the value that's reported out by the company, all right? So that's really the kind of summary of this here. Okay. So again, there's more practice here for you guys to be able to take your time and work through. And then, of course, more experimental questions here. All right, so there's some calculating and some just kind of basic knowledge here. Like, for example, which of these suffers from the lack of a control group? All right, so reading these and really evaluating, does it have a control or does it not? All right, knowing what the most important factors in an experimental design are. All right, and then obviously here, this one's actually asking you to calculate your 95% confidence interval. Okay, so same thing. All right. So again, wrapping this up here, looking at our study sheet quickly, it's going to be a lot of the same things I've been saying. All right, so looking at the control, randomization, and replication, okay? And there's a lot of examples throughout that entire unit that you could have written some of these down. You could have came up with your own here, all right? So we walked through an example of having poor control. We walked through an example of having poor randomization and poor replication, all right? And again, all of those don't mean that your test is completely bad. It just means that it's hard to make conclusions based on that because we're not sure. Right, we're not sure if we have introduced bias by not constraining and one of those factors. All right, and then of course this gets really, really important here. So our sample mean, all right, when we're trying to calculate our standard deviation, right? We're trying to calculate our standard deviation and figure out if our sample mean fits inside the confidence interval, right? So we have to use this formula here of S equals sigma over square root of n. And of course, the sigma up here is the reported out standard deviation. N here is our number of objects. And what this S is also a standard deviation here. So, but this is the standard deviation reported out to us from the company. And what this gives us is our standard deviation of our sample, right? Our standard deviation of our sample mean. All right. And then of course we walked through a couple of those problems there. And again, really getting to the point of, okay, if we're evaluating if it works or not, look at the 95% confidence interval. If it falls in, great. It's indication that it's true. If it falls out, it's indication that it's false. And regardless, in both of those cases, it's probably going to require repetition in order to make sure that that's true. Okay. Looking forward here with our checkup. Of course, it's going to be a lot of questions based on how could we make this better? All right, how could we make this better? All right, and something I want to point out here, all right, is it's asking what would be the most and the least conclusive. All right, in both of these cases here, it's always going to be better to have more repeats, right? So more repetition is going to give you more confidence and be able to make a more conclusive argument, all right? So obviously to be more conclusive, we'd want the highest number. To be least conclusive, that would be the lowest number, all right? So don't let that one trip you up, okay? Then talking about here, determine the expected mean of a sample of that population. So of course, right, you've got to use that equation S equals sigma over square root of n. So pulling out here what those different values would be. Okay, pulling out what those different values would be. Right? So again, pulling out what those different values would be and indicating this 95% confidence by being able to do the calculation here. And again, of course, I love that they write it this way. So when we talk about a 95% confidence, again, you have to write it with the average value plus or minus your standard deviation. All right, you don't just write plus or minus the standard deviation, right? You got to have the whole package here. All right, and then finally, given the mean and standard deviation and the sample size, determine which group is within the confidence interval, right? So doing that calculation and then of course figuring out which is inside that 95% confidence interval. And of course, doing the same thing here, except we're looking for which ones are outside of the confidence interval, all right? So ultimately, that's what it adds up to is, can you be able to do a 95% confidence interval and make some conclusions based on that, assuming that the experiment is done perfectly well. All right, so of course here you've got this 4.7 quiz, all right, and the extra credit practice opportunity if you want it, all right. Which brings us then to 4.8 here. So in 4.8, we've talked about a lot of things, all right. And if we kind of do, it's like this funny. If we look at the review here, okay, you should be able to answer some of these questions here. And obviously there are basically 7 pages, right? Each page belongs to a different lesson throughout the unit. So if you're confused on something on, this page, you go back to the lesson that it corresponds to. All right. So basically, we started off with a review of graphical analysis of data, and they call it a review, but if this was your first time, then it was obviously an introduction to graphical analysis. All right, so we talked about what is statistics, we talked about descriptive versus inferential statistics, numerical versus categorical, the different ways of describing the data, right? So what kind of graphs can we generate? And then obviously within those graphs, we talked about the distribution, the shapes of them, talking about how to measure the center and then measure the spread, right? So you can go through this and click on these guys here and look at that, right? And then we moved on to a numerical analysis of data, right? So talking about the central tendencies. So the central tendencies being like spread, the distribution, where it's located, the mean, the mode, right? The median, right? All of that stuff we also talked about. We talked about our 5-number summary, including our quartiles in order to make a box and whisker plot. And then we talked about how do we modify a box and whisker plot if we have a really far outlier, all right? And then, of course, the last thing we focused on was finding standard deviation of a data set, right? Finding that standard deviation of a data set. And as you found out, obviously that last part comes in extreme handy here, okay? So then we spent a unit talking about how do we gather the data and how can that be used to make inferences outside of the data set that we have, right? We talked a lot about that. We talked about random variables and how do we look at them, and again, what does a normal curve look like? What's our rule for, data inside, right? And again, that's that 2 sigma rule. So again, looking at this and how do we figure out if there's a variable that has an effect, all of that. And then, of course, we spent a day focusing on experimental design. So our control group, looking at our sample size, all of those things in order to reduce our bias, right? And then we spent yesterday, of course, evaluating published reports. So looking at how do we publish report? How do we publish something with unbiased? How do we look at something and make sure that it's telling what we needed to tell in a way that is showing all of our data? Did we do the analysis correctly, right? Et cetera, et cetera. And then finally, we looked at an application of our statistical techniques, right? So really evaluating our control group, our sample size, our randomization, and then being able to interpret data being given to us from outside sources here, Okay, really being able to interpret data from outside sources here. All right, so hopefully, again, you have a pretty good understanding, at least maybe as an intro to statistical analysis. All right, how can we look at things and do some basic stats on them to see if what we're being told is the truth, or if companies are stretching a little bit, right? Or for us to be able to display our data in a way that is ethically correct, but also gets across the points that we're trying to make here. All right. So there is, of course, a checkup here where if you go through it and you can do those practice problems, you're going to be good for your CST. All right, so again, I suggest at least taking a look at this, if not doing some of them, because it's going to tell you pretty much what you can expect here for your CST. All right, so again, you need to do this quiz and you need to do this unit test here. So CST only. All right, our CST only here. All right, now if we go into unit 5 here, all right, so in unit 5, if we look, it's not a super short unit, so we've got lesson 5.10 is going to be the last one. All right, so I'm going to try to cover at least 1, maybe 2 today, and then of course we're going to try to cover 3 tomorrow. So again, whatever we don't cover gets to be or gets pushed to be your weekend homework here. All right, so if we look quickly here at this thing called trigonometry, all right, we can do this overview here together.
What makes the notes on a piano different from each other? How does a robot's microprocessor help it move? How is a nail in a tire like the moon orbiting the Earth? As you go around in a circle, how does where you are relate to how much you've spun? How could you represent this relationship? How could you visualize the relationship on a graph? Circles and right triangles seem to be very different. So how can the relationship between them help send a person into space, model the shape of your DNA, or tell you the best time to go fishing? Trigonometry lets you take digital photographs, watch a high-definition video of your favorite team, and even predict the stock market. From its name, you might think that trigonometry is only about triangles. Triangles are certainly a good place to start, but as you continue on, you will see that trigonometry is a diverse and beautiful subject.
Okay, so that's kind of your introduction to trigonometry, all right? And usually people think trigonometry, they think, of course, triangles, they think shapes, they think angles, and so what better place for us to start than at right triangles here, okay? So if we look at right triangles, I don't remember if we use this exact example or not, but we can figure out
during a typical day.
We can figure out how tall a tree is without actually having to know all of the parts here. All right, so if we listen in.
The position of the sun in relation to an object will determine the length of a shadow cast by that object. Here you see that as the sun moves, the length of the tree's shadow can change from very short to extremely long. In a situation like this, you can calculate the length of the shadow by simply walking the distance. You can also estimate the angle as shown. Is this enough to enable you to calculate the height of this tree? It turns out that the answer is yes, it is. To begin to understand how such a calculation would be possible, you must first gain an understanding of trigonometry. By the time you finish this lesson, you will be able to answer all sorts of questions about distance, angles, and lengths as they relate to right triangles.
Okay. And again, this is going to be important because they'll reference it, of course, later on as well. All right, but I want to highlight a couple things as we go throughout this study here. All right, so of course, right triangles are called that because it has a right angle, and a right angle is something that measures 90 degrees here. All right, so it measures 90 degrees, and if there's one 90-degree angle within the triangle, it's called a right triangle. All right. And right here we have a triangle, and we label the sides A, B, and C. All right, and C is always the angle that is across from this 90-degree angle. All right, so A and B are what we call the legs of our triangle, and C is, again, opposite of our 90 degrees, and it's called the hypotenuse. All right, it's called the hypotenuse. All right, so our formula then for Pythagorean theorem is, oh, I thought they would show it there. I guess we got to type it in here. All right, so our formula for Pythagorean theorem is a squared plus b squared equals c squared. All right, and I'm not quite sure how much my sophomores have experience with this, okay, but there is a formula called Pythagorean formula, Pythagorean theorem formula, and it's where it says a squared, so this length squared plus this length squared equals this length squared. All right, and of course, if you see it as with an up caret 2, right, that means to the power of 2 as well. Okay, so you're going to see this formula a lot there. All right, and of course, it says a squared plus b squared equals c squared, and what it's really saying here is that it's got 3 positive integers. Okay, so a, b, and c are all positive values such that they make a right triangle with lengths a, b, and c. All right, so they're making a triangle with 3 sides, right, positive sides, and any triangle that fits these parameters will satisfy our relation of a squared plus b squared equals c squared. All right. So what is the significance? Why is this so important here? And it's going to be so important because that's saying that if we know 2 sides of our triangle, we can figure out the third one. We can figure out an unknown length here. So let's take a look.
The Pythagorean theorem tells us that the sum of the squares of the lengths of the legs is equal to the square of the hypotenuse. In symbols, this is written as a squared plus b squared equals c squared. Geometrically, this theorem tells us that if we add the areas of the 2 smaller squares, we will get the area of the largest square in this diagram.
Right, and again, what they did here is they made it squares because a squared, when you do the area of a box, you take its height by its width. So this would be like saying a here and a here. All right, so if this part confused you, all they did here was they said, okay, in order to get a squared as my area, that's talking about a box. That's talking about length times width where they're the same thing. Okay, so don't let that confuse you.
Now assume that we only know the length of 2 sides of a right triangle, and we want to know the length of the third side. We can use the Pythagorean theorem to solve for the third side. If we solve this equation for c, we find out that c equals plus 5 or negative 5. Ruling out negative 5 is impossible for a length. We see that c equals 5.
All right. Again, point I want to highlight there that he mentioned.
As this example shows.
Sorry, that he mentioned here. Okay. Negative values got the negative values got thrown out. Okay. Again, I know that we were talking a lot in quadratics about how when you take the square root, you have a plus and a minus answer, right? That means you can have a plus and a minus answer. But part of the theorem states that you have to have all positive values here. We can't have a negative 5 length. So obviously it makes it that positive one.
It is important to remember that the Pythagorean theorem is true only for right triangles.
Okay, so that's a huge thing. All right, so it's only true for right triangles. We'll talk about if it's not exactly a right triangle later, potentially. But again, we're talking about right triangles only is what this rule works for every single time. Okay, so then if we were to look at this problem here, we're supposed to run a football field that measures 160 feet by 300 feet. After school, our coach makes us run 5 miles. All right, so we have to run along this path here, and hopefully what you're noticing is that it's a triangle that has a right angle. So this is a right triangle here. All right, so the question is then, how many times would we need to travel this path in order to run 5 miles? So obviously here, this triangle is showing us our path. Okay, so the first step we'd have to do here is figure out what is this length here. Okay, what is this length here? Because we're going to run around it, so we need to know how far one lap is. Okay, so we need to solve for this missing one here. All right, and we know we're going to do a squared plus b squared equals our c squared here. All right, so we would add a squared plus b squared together and take the square root, and that's going to give us our 340. Okay, it's going to give us our 340. All right, so now that we know this here, we can know that when we add them all together, okay, when we add them all together, we're going to get how far one lap is. All right, so one lap around this is 800 feet. Okay, and then the final question is that we need to run 5 miles, right? We need to run 5 miles. So right now we're dealing with feet here. So we're going to have to look at how many feet are in a mile, right? So there are 5,280 feet in a mile. Okay, and we've mentioned something like this briefly in for my sophomores, but I know for my juniors we've talked a ton about this. All right, but if you have feet in a mile or feet per mile, you write it as feet under 1 mile, right? Feet under 1 mile. All right, and here we said one lap is 800 feet, or 800 feet in a lap. Okay. So what we can do here is we can do our unit analysis or dimensional analysis, unit cancellation here, right? Where we basically take and we say 5,280 feet per mile. Well, I know that I have one lap is 800 feet, and feet will cancel with feet. And what this is saying is 6.6 laps per mile. Okay, so it takes 6.6 laps to do 1 mile. All right, and then obviously here the last step is if there's 6.6 laps in a mile, how many laps will you do to run 5 miles? Well, you just multiply this number by 5. Okay, we multiply our 6.6 laps per mile by 5 miles, and we are left with 33 laps here. Okay, and again, take some time to work through that on your own if you need it. All right, and then there are certain specific right triangles. Okay, there are certain specific right triangles to keep in mind here. All right, so the first one is this one called a 45, 45, 90. All right, 45, 45, 90. All right, and it has some special properties here. Oh, okay, and again, it's called a 45, 45, 90 because that's talking about the degrees of the angle. So you've got a 45 degree, a 45 degree, and a 90 degree, all right? And we'll start here, but basically what they're showing here is a box, and each of these boxes start with a 90 degree angle, and then they're gonna, of course, show this cutting this 90 degree angle in half, giving us our two 45s.
Since the diagonal of a square bisects, divides in half, the angles of the square, the angles formed measure 45 degrees as marked. This kind of triangle is referred to as a 45, 45, 90 triangle. You can use the Pythagorean theorem to write the relationship between the legs and the hypotenuse of this kind of right triangle.
Okay, and let me point something out to you here. All right, they wrote both of these legs here as value A. And the reason that they do that is because they have the exact same angle. So since they have the same angle, they're going to have the same length. All right, so you can just write both of these lengths as the same variable here if they have the exact same 45 degree angle. And again, that's one of the special characteristics of this 45, 45, 90 triangle.
As these calculations show, each leg of a 45, 45, 90 triangle is equal to 1 over the square root of 2 times the hypotenuse.
Okay, so carrying out the Pythagorean theorem here and solving for A this time, you can write this entire triangle in terms of your value C here. All right, you can write everything in terms of your value C here. All right. So this is just another way of looking at the same triangle. And again, all they did was they solved for the Pythagorean theorem, they simplified, and then they isolated the A value. All right, so nothing that you don't know how to do already. All right, so then moving on here, we have a 30, 60, 90 triangle, a 30, 60, 90 triangle. All right, and so to start this one, it's easiest to start with what's called an equilateral triangle, and hopefully you know a little bit about this, but basically equilateral means that they're all equal or all the same length. okay? So they're all the same length, they're all the same angle degree. All right, so it's a 60, 60, 60. They all have the same side length. We start with that. And then obviously we need to turn it into our 30, 60, 90. So we're gonna split right down the middle in order to give us that perfect right angle. And we'll split our 60 degrees in half in order to make that a 30. All right, so let's take a look then. What happens?
Consider this equilateral triangle with side length C. Since the altitude of an equilateral triangle bisects the 60 degree.
Okay, notice here, C over 2, right? This length here that used to be our value for C now got cut in half, so it is now C over 2.
Angle and is a perpendicular bisector of the opposite side, you obtain a 30, 60, 90 triangle. This calculation shows that the short leg of a 30, 60, 90 triangle is 1/2 times the hypotenuse. To find the length of the longer leg, you can use the Pythagorean theorem to write the relationship between the legs and the hypotenuse. As these calculations show, the longer leg of a 30, 60, 90 triangle is equal to the square root of 3 over 2 times the hypotenuse.
Okay, again, nothing that you don't know how to do. All right, all they did was they plugged it in our a squared plus b squared equals c squared formula. They executed some algebraic simplification, right? Combined like terms, isolated b by itself, and then the only other thing here was they got a plus or minus answer, right? And they threw out the negative answer because, of course, with our triangles here, we've got to deal with positive side lengths here, all right? So again, you don't have to memorize this. You just have to know that there is a relationship, and you have to be able to understand how to get to that relationship here. And of course, it's the same thing. Start with something that you know, right? And then solve from there. All right. And then another type of important triangle to notice is this one called similar triangles, okay? It's called similar triangles. So what they are is they're triangles who have similar angles, right? So they have the same angles, and the lengths then are going to be proportional. Okay, the lengths are going to be proportional. All right, so we'll do an example of this for sure. I know that, but basically this is saying angle A is going to be the same as angle D. All right, and if there's a ratio, right, of this side length, it's going to be the same ratio from triangle to triangle. So maybe this triangle is 1 and this triangle is 1.5 times that triangle. So every length would be 1.5 times larger, right? There is a relationship and it's proportional to each other. Okay, they can also be called congruent triangles. All right, congruent triangles. All right. So there is a difference between similar triangles and congruent triangles. All right, so the difference being corresponding angles of similar triangles are congruent and the side lengths are proportional. Okay, so in in similar triangles here, the angles are the same and the side lengths are proportional. All right, but in congruent triangles, they're absolutely the same. They have the same angles and they have the same side lengths. Okay, they have the same angles and the same side lengths. All right, so looking at the similar triangles and proportions. Okay, so again, what this is saying here is that these two, that squiggly line means is that they have a relationship, right? They're proportional to each other. All right, so if we look at our congruent angles, it's saying angle A is similar to angle B, or sorry, to D. B is equal to D. Oh my gosh, E and C is equal to F. All right, and what this means is the squiggly line and the equal sign means it's approximately equal to, right? It's approximately equal to. All right. If we look at the proportional sides, what this is saying is length AB is proportional to DE. BC is proportional to EF, and AC is proportional to DF. Right? That's what this is saying here, is again, these are proportional to each other. So then if we look at our equation of proportions, right? So if we look at our equation of proportions, B to C, again, is the same thing like E to F, A to C over D to F, right? Those are going to be equal to each other, right? Those are going to be equal to each other because they are proportional, all right? And again, I don't know how much my sophomores have done with any of this here, but if we look at trigonometry here, moving forward with that, okay, there's 6 basic functions that are going to be crucial for the study of trigonometry and calculus moving forward here, right? And what they are sine, cosine, and tangent. Those are kind of your main 3, all right? And then we have cotangent, secant, and cosecant. All right, and these 3 are based off of the original 3 here. All right, and we'll talk obviously more about these here. All right, but in general, what we're gonna do here is we're gonna have to use the ratios of the sides of our right triangles. Okay, so we're gonna have to use our right triangles in order to solve for these different functions here. Okay, and we're gonna go through this obviously more specifically here, but there's a saying that my sophomores, if you've never heard it, you need to write it down, live it, learn it, love it, because it really, really does help you understand these functions here. All right, and the phrase is so katoa. That's what this is saying here, so katoa. All right, and what this is saying is sine, right? Our sine function is equal to our opposite over our hypotenuse. Our cosine is equal to adjacent over hypotenuse. And tangent is equal to opposite over adjacent, right? And that's exactly what it's saying here. All we did was we took the capital letters of the main part. So sine, opposite, hypotenuse. So katoa. All right, again, going to be really, really helpful for you moving forward here. All right, so now knowing that we're dealing with our opposite, adjacent, and this word hypotenuse, again, we need to be able to understand what that looks like on our triangle here. All right, and beside the hypotenuse, right, opposite and adjacent are going to be determined based on which angle we're dealing with. Okay, it's going to be determined based on which angle we're dealing with. All right, remember, our hypotenuse is always the one that's opposite our 90-degree angle here. So that one's never going to change. But our opposite and adjacent, those might, right? Those might. So if we look here, this little symbol, remember, again, means theta, right? And that stands for our unknown angle. All right, so theta here is the angle that we're looking at. So if we're looking at the sides of our triangle, this one is still our hypotenuse because it's across from our 90 degrees. Now this side length, BC, is now our opposite because of course it's opposite the angle we're looking at. All right, and then AB here, our last one, is adjacent. All right, adjacent because it's right next to our angle. All right, so that would be how we label this triangle here. All right, and of course, like I said, it depends on the acute angle theta. All right, it depends on the acute angle theta. All right, so then looking at some of these problems here, I'll do 2 and leave the rest for you guys, but which side is the hypotenuse? Obviously, it's the one across from the 90 degrees, so that's going to be letter B. All right, and then it's saying, what should we label A and B as? Well, if you look here, this is our angle, so we go across from our angle, so side B should be labeled as opposite, and side A should be labeled as hypotenuse. Okay, so 3 and 4 also ask you similar questions, again, opposite or adjacent. Again, the key is figure out where the angle is that you're looking at and the side in relation to that angle there. Okay. And now what we can look at here is these trigonomic ratios, right, are 6 trig functions here. All right, so first off, if we look, we've got our sine, and if you remember that phrase, so katoa, this is our so it's sine equals opposite over hypotenuse. That's what it means here. So sine opposite hypotenuse, SOH. Okay. And then we can go to our cosine here. All right, and our cosine is our CAH, cosine adjacent over hypotenuse. All right. And then our tangent here is opposite over adjacent, right? TOA, T-O-A, opposite over adjacent. All right, so that's how we look at these three trigonomic expressions here. All right, now we're dealing with the other three. So we've got this thing called cosecant, secant, and cotangent. All right, and I wish it was all written down in one place here, but cosecant is written as hypotenuse over opposite. All right. Secant is written as hypotenuse over adjacent. And then cotangent is adjacent over opposite. All right. Adjacent over opposite. And these ones here might not be as obvious, but if we look at these three in relation to our original three, what we can do is draw some similarities here. All right, but before we jump over, tangent, okay, is our opposite over our adjacent. It's also equal to sine over cosine. Okay, it's also equal to sine over cosine. All right, so that's a nifty, handy trick there sometimes that we can use. Okay, but looking at this here, okay, there's a relationship that cosecant is just 1 over sine. Secant is 1 over cosine. And cotangent is, lo and behold, 1 over tangent. Okay? So obviously tangent and cotangent, they're pretty easy to remember that they're matched up there. All right? But the way that I remember sine is with cosecant is that this one starts with an S, so its opposite has to start with a C. This one starts with a C, so its opposite has to start with an S. All right, that's just a fun way of helping you maybe get these down a little bit faster. All right, and basically, cosecant is 1 over sine. So what we did for sine, our opposite over hypotenuse, we just flip it and put our hypotenuse on top. Right, and it's going to be the same for our other two functions here. Okay. So then, of course, I'll let you guys do this one and kind of test your knowledge here. But my personal suggestion is start with your friendly phrase SOHCAHTOA and then try to remember which one is opposite for our original three trig functions. Okay, that's kind of my help there. All right. And then it's asking what triangle do I use? Okay. I don't know why this would be a question that you're asking yourself here, but in general, when you're looking at triangles, okay, we have now the ability to look at any side, any angle, right? As long as we have some information here, okay. But of course, then here, like I said, the values should depend on the angle. Okay, the values will depend on the angle. All right. So again, you could have multiple triangles that have a similar side length, but of course it's always going to depend on the angle. It'll depend on the angle. All right. So of course, if we're looking at angle here, all right, versus our angle in there, versus our angle out here, again, it's gonna depend on our angle. All right, but something that you should hopefully notice here. Right now, the side lengths are changing. Okay, the side lengths are changing. But our ratios between our opposite over hypotenuse, adjacent over hypotenuse, those are not changing. Those are not changing. And that's the beauty of this. All right, that's the beauty of this. Even if we rotate it, I don't know why. Even if we rotate it here, okay, it's not changing the values. It's just changing where it's located, okay? So again, this is just showing you that you can have those similar triangles like we talked about, right, where they have a relationship, all right? But it doesn't matter when you're dealing with those trig functions because they're all in relation to each other, right? Opposite over hypotenuse. If I make this 1 time smaller, or I make it half the original size, it halves all of those lengths. So this relationship still stays consistent. Okay, and then we go from understanding our ratio to our trigonomic functions, right? So turning them actually into functions here.
Consider two similar right triangles. Clearly, triangle ABC has larger side lengths than the corresponding sides of triangle DEF. What happened?
Okay, well notice he said similar triangles. Okay, so similar triangles have lengths that are proportional to each other, but they have the same angles. Okay, they have the same angles.
Happens if you use both triangles to define the function sine. You can use either triangle to determine the value of sine for the angle theta. In each case, this is just opposite over hypotenuse. For sine of theta to make sense, these two expressions must be equal. This is guaranteed since BC over AC equals EF over DF is one of the equations of proportion for similar triangles. Sine of theta depends only on the angle theta and does not depend on which triangle is used. The same argument will show that this is true for any of the 6 other trigonometric functions.
All right, so again, it's based on the angle, not based on the specific triangle. All right, so then if we can say that here, it's based on the angle, there's some common values here that we can fill out for our different functions for some familiar angles for us. All right, so we can look at calculating these functions. And again, if you see something like this, what this is asking is saying sine of theta, where theta equals 30. So this is asking you what is sine of 30 or what is cosine of 45. All right, so if we look at filling in this table here, we can first start off by looking at our 45, 45, 90 degree triangle, right? So, because one of the angles was 45 here. So it was asking us what was our answer for the 6 trigonomic functions of a 45 degree angle here. So let's take a look.
Start with the 45, 45, 90 triangle. The fundamental property of 45, 45, 90 triangles gives these ratios between the side lengths.
Okay, so again, how we figured this out was remembering that these are both the same sides, plugging them into Pythagorean theorem both as the same variable, and then of course solving for that variable. All right, so that's how we got this 1 over square root of 2c. All right, so now if we want to look at this, we can look at our sine function, which is opposite over hypotenuse, right? So our opposite over hypotenuse is this 1 over square root of 2c over c. Well, that gives us 1 over square root of 2. Lo and behold, cosine is going to do the exact same thing, right? 1 over square root of 2c, it results in this 1 over square root of 2. All right, and then tangent is the only one that's slightly different here. Okay, it's going to put our opposite over our hypotenuse, but regardless, they're the same value, so it's going to give us an answer of 1 here.
Since cosecant, secant, and cotangent are simply reciprocals of sine, cosine, and tangent, you can now find these values easily.
Right, so all we did for this was we flipped the numerator and the denominator, and square root of 2 divided by 1 is just square root of 2, so that's how we wrote it here. All right, and obviously 1 divided by 1 is still going to give us 1. All right, so figuring out these first 3 then give us an easy way of figuring out our last 3. Okay, and then we have obviously all of our answers for our 45 degree angle. Okay, we have all of the answers for our 45 degree angle. All right. So then looking at our 30, 60, 90 triangle. Looking at our 30, 60, 90 triangle. Oh gosh. We can use our 30, 60, 90 triangle and complete the table there, all right, using the same logic. All right, so again, just looking at what we had those side lengths listed as, and then of course going through the different operations of opposite over adjacent, opposite over hypotenuse, right, all of that stuff. All right. So then looking here, we can actually use this to evaluate our trigonomic functions.
Suppose you know that sine of theta equals 1/4. To find the values of the other 5 trigonometric functions, start by drawing a right triangle and labeling the angle theta. Here we assume that theta is acute. Since sine theta equals 1/4, you can write a 1 on the side opposite theta and a 4 on the hypotenuse. You do this because you know that the ratio of those sides has to be 1/4.
Okay, and again, that was something that would be given to you, right? So it says, okay, sine of theta is equal to 1/4. They're asking us to evaluate everything else. So again, we draw a right triangle. If we're dealing with sine, cosine, tangent, it is talking about a right-hand triangle, of course. All right, so we can draw this triangle, and we can draw it approximately to scale and know that, okay, sine is equal to opposite over hypotenuse. So the opposite of this angle has to be 1. All right, and again, you could have put theta here or put theta there. The only place you can't put it is where that 90-degree angle is. All right, so
now you need to calculate.
Apologies. So when you're drawing this, okay, when you're doing your work, if we were in class here, right, maybe my group always likes to draw it here, but maybe somebody else's group likes to draw it there. All right, so it doesn't really matter. There's no constraints on it as long as you're able to follow the opposite over hypotenuse and adjust accordingly.
Now you need to calculate the measure of the third side, labeled A. This is where the Pythagorean theorem will be used.
Okay. Oh, apologies. Sorry, I got lost. All right, so if we look here, all right, so this is asking us to do our Pythagorean theorem here. So that's saying a squared plus b squared equals c squared. So a squared plus 1 squared equals 4 squared. All right, so that means that a squared here is equal to, I think it's 3 squared, 15. All right, sorry, I can't do basic math today. So basically, it's going to be 15 here because, again, we have 4 squared gives us 16 minus 1 squared, which is 1. So that gives us our value here of 15, all right, for a squared. So then in order to get a by itself, we take the square root of 15, and so that's what gives us our side right there. All right, and now that we have all 3 sides of our triangle, it's
now that you know all 3,
it's very easy for us to figure out our cosine, secant, cosine, sine, tangent, cosecant, secant, tangent, all of the other 6 trigonometric functions there. We can figure those out. Okay, so then this is a good practice problem, and I know you guys have problems with drag and drop, so I'll do this one with you. All right, so this is saying, again, assume that sine of theta is equal to 2/7. All right, so theta right here is our angle. So sine means opposite over hypotenuse, right? So katoa. So this is saying our opposite is 2 over our hypotenuse of. Okay, sorry, I don't know why I kept doing that. All right, so our opposite over our hypotenuse are 2 and 7 here. All right, then we have to figure out this last value here. All right, and again, this would be where we use our Pythagorean theorem. All right, so we would have a squared plus 2 squared equals 7 squared. So that's 49 minus 4. And then we take the square root of it. So that would give us our 45. All right. So we have this entire triangle. Now that we have this triangle, we can do our different trigonometric functions. So again, personally, I start with the fantastic 3 here, our sine, our cosine, and our tangent. So sine is, of course, this over that, right? Our opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. So 2 over square root of 45. All right. And then again, remembering that sine is matched up with cosecant, cosine matches up with secant, and tangent matches up with cotangent. It's just the reciprocals. So since sine is 2 over 7, cosecant is 7 over 2. All right. Since cosine is square root of 45 over 7, this is going to be 7 over square root of 45. And finally, of course, this is 2 over 45, so flip it, square root of 45 over 2. All right. And again, you can go through that and take your time and try that again if you'd like, but that's essentially how this is working here. Okay. So of course, then here, if we go back to our tree problem, we can talk about now how we can solve for the height of our tree here using
You notice that the tree is casting a shadow and that the length of the shadow varies depending on the position of the sun. At a particular moment in time, you estimate that the angle between the ground and the line that connects the tip of the tree to the tip of the shadow is 55 degrees. You measure the distance from the tip of the shadow to the bottom of the tree to be 20 feet. Remember that you are trying to find the height of the tree, so call that x. Since tangent is defined as side opposite over side adjacent, you see that tangent of 55 degrees is x over 20. Use your calculator to approximate tangent of 55 degrees and then solve for x. In the end, you find that the tree is roughly 28.6 feet tall.
Right? So again, using what we have and what we know. So this is maybe for one of our first examples here. It's telling us exactly tan 55, right? And we know tangent is equal to opposite over adjacent, right? So x over 20, all right? And so again, you can plug into your calculator tan of 55 degrees, right? You can actually go in and plug that in. That's in your graphing calculator abilities, all right? But you have to make sure, of course, double check calculator tips here. You have to double check to make sure that you're in the correct calculator mode. All right. So you have to make sure that you're in the correct calculator mode. So again, of course, if you're asked to find sine of the angle of 37 degrees, okay, on your calculator, you need to make sure that your calculator is in the degree mode. All right. So you hit mode, you scroll down to degree and make sure it's selected. Okay, then you press the sign button, which is above all of our numbers. You type in 37, you just hit enter, right? So not anything terribly difficult here, all right? Not anything terribly difficult. It works the same thing for cosine and tangent, all right? So of course then here, right, we talked a lot about Pythagorean theorem. We talked about our different angles for our specific triangles, and then talking about our trigonomic ratios for sine, cosine, tangent, cosecant, cosine, and cotangent. All right. So then here, of course, is some practice problems for you guys to go through. Since we're running out of time, I'll fly through this. All right. And again, a lot of this is going to be repetitive here. It's finding the missing side, right? It's finding the missing side using what you know. So a lot of Pythagorean theorem here. All right. A lot of Pythagorean theorem. All right. And then understanding the relationships between the new trigonomic functions that we've learned. All right. So this study sheet here is going to be super important if those relationships and all these equations are new to you. Of course, really rely on this study sheet to help you. But basically, remember we have our hypotenuse, which is our value across from our 90-degree angle, and then we have two other sides, which are known as our legs. Right, and what we can do then is we can square our legs, add them together, and that's going to give us a square of our hypotenuse, right? Or what this is saying here is a squared plus b squared equals c squared, all right? And the Pythagorean theorem cannot be used for any other triangles than right triangles, right? So it has to have this 90-degree angle here, all right? And you can go through and solve for this here, right? And we talked a lot about the specifics of our different triangles, right? So what were the lengths for a 30, 60, 90 versus a 45, 45, 90? Then we talked about similar triangles versus congruent triangles. Really the difference being, are they identical or are they proportional? All right. And of course, then two similar triangles have this thing called a scale factor, which is that common ratio between the the different triangles here. All right. Then we looked at, finally, the trigonometric relationships of our different functions here, our 6 different functions. And that has to deal with what's adjacent and what's opposite based on the angle that we are looking at here, okay? And from there, of course, you can write all of our different relationships that we know, and we have some standard values that can be easy. We can either recalculate them, replug them in, find them out, whatever. But this right here is going to be a big helper if you can try to just know where these are, so that you can use them and not have to memorize them, all right? So again, of course, doing some of these here. All right. And then finally, our checkup is, of course, a lot more practice problems about solving for our different lengths, right? So finding the different lengths of our triangle, really making sure that you have your calculator skills down, and understanding the relationship between those trigonometric functions here, okay? So really looking at some of these problems here. All right, and again, all it's basically essentially boiling down to is right triangles, right? It's talking about right triangles. So when you get to something like 19, okay, well, actually 19 is not what I was thinking, but if you get to a word problem here, like this one, perfect, 14, okay, all you have to do is draw a picture, right? And the picture should start with a right triangle, right? Because that's what we're dealing with in this entire unit here. So that's going to be my key to help you out. Draw yourself a picture, right? And the picture should start with a right-hand triangle. All right. So then that kind of brings us to the end of class here. So you're going to have this quiz here, 5.1 is our introduction to trig. All right, so that's what we've covered today. We covered 5.1 and we covered our last 2 units in unit 4. So we covered 4.7, which has that quiz, and 4.8, which is your unit test here. All right, so again, really trying to catch up and stay ahead as much as possible is going to be beneficial for you. Because again, because today we covered 5.1, tomorrow we're going to try to cover 5.2 to 5.4, right? Which then leaves us about 4 or 5 lessons for this weekend here. All right, so again, that's just kind of a prequel to get you ready for what's coming. All right, so again, if you have questions, let me know, reach out, please. I'm here to help you. But other than that, guys, I'll see you then tomorrow, or juniors, I'll see you later this morning. All right, have a good rest of your day. Goodbye.